Oh my goodness, I love problem number 6. It was probably one of the only interesting ones in the quiz, in the exam. But it was definitely one of the more interesting ones. And it's kind of hard to know unless you've seen this kind of stuff before. And there was a problem like this we did on one of the quizzes, or several of the quizzes, that had similar ideas. And so the idea was to try this substitution. So we say, okay, what if we call u equal to pi over 2 minus x? Okay, then du would be equal to negative dx. And I'm using this as a complementary angle to see if I can switch the sines and the cosines and see what happens. This becomes the integral, this becomes the square root of cosine. Instead of x, I have pi over 2 minus u, because the dictionary here would tell you that if I move x over there, that becomes x is equal to pi over 2 minus u. And so that becomes that. This becomes the square root of sine of pi over 2 minus x minus u. And of course this becomes the square root of cosine of pi over 2 minus u. And this becomes dx, which becomes negative du. And the cosine of the complementary angle turns out to be just the sine of the angle, sine u. And then the sine of the complementary angle becomes just cosine of u. And the cosine of the complementary angle becomes sine of u. And of course I had a du here, I had a negative, and I can go on and plug in my values, my limits here. These were x limits. These were x limits. So I could pour the dictionary here, my blue dictionary, and try to figure out the limits. As I plug these into the dictionary, what do I get? So when x is pi over 2 here, I get that u is equal to 0. When x is 0, I get that this is pi over 2. And so then I can flip these and change the sign to give me the integral from 0 to pi over 2 of the square root of sine of u all over the square root of cosine of u plus the square root of sine of u du. So my original problem, I could call this I if you want. I is equal to that. It's equal to this, it's equal to this, it's equal to this. I is equal to this. And the trouble with the substitution is that it really doesn't get me that far. In fact, it almost looks like the same problem again. This doesn't look any easier than the original one. In fact, it looks just as hard. In fact, it looks almost identical. In fact, we can use that similarity to do something amazing. That one is very, very hard by itself, and this one is just as hard by itself. But look what happens when you add them. I is equal to the square root, or the integral square root of cosine of x dx all over the square root of sine of x plus cosine of x from 0 to pi over 2. And that same I is calculated to be the integral from 0 to pi over 2 square root of sine of x, and the same denominator, sine of x plus cosine of x dx. But here's the amazing part. We should do the amazing part in amazing red. If you add them together, you get that two i's. Each of them by itself is really, really hard. That's hard and that's hard. But when I add them together, I get the integral from 0 to pi over 2 of the square root of cosine of x plus the square root of sine of x all over the exact same thing, square root of sine of x plus cosine of x. And lo and behold, this becomes 1, and so I get that 2i is equal to the integral of dx, just a 1 there, from 0 to pi over 2, which is obviously pi over 2. And yippee-ki-yay, I get that the original integral is equal to pi over 4. See why they pay me? You see why they pay me insane amounts of money? Beautiful problem. There's so much creativity in here, and that's why I like it. And we've seen this sort of idea before where we use the complementary angle. It's almost like the boomerang effect when you get on some of these integrals where you end up with exactly the same thing. Here we didn't end up with the same thing, but similar enough to where we could do something with it. Very, very nice technique here. A little creative. Alright, let's go on and do the next problem. Yeah, come back for some more.